بسم الله الرحمن الرحيم. اليوم إن شاء الله بنغطي Unit 5 tutorial. Probably for the next two classes, we'll see how we progress on these questions. طيب هو there is no solution prepared and I did not check the tutorial beforehand, so we'll do it together. So if you have any comment or any question, please stop me anytime. طيب, let's start with the first question. Apply structural modeling in the design of the digital circuit given by the Boolean equation y equal to a bar b bar c bar a b bar c bar a b bar c. So that's min term 0, min term 4, and 5. So 0, 4, 5. This time use Verilog's built-in gate primitives in your model instead of module instantiation. For the latter, refer to lecture 5. طيب. We want to implement this equation using structural modeling and only using built-in gate primitives. ايش هي built-in gate primitives؟ اللي هي ال AND, ال AND or XOR, NOR, NAND, and so on. Okay, so let's head over to our code, our Verilog Editor. First, let's draw the circuit so we can name the wires and then use the built-in gate primitives. طيب. So the function was y equal to min term 0, min term 4, and min term 5. Okay, which is a bar b bar c bar, or a b bar c bar, or a b bar c. So from the equation, we need 3 AND gates. Each AND gate is 3 input, and 1 OR gate with 3 inputs. OR gate for the output. This is why I have a bar b bar c bar. I have a b bar c and a b bar c bar. Okay, that's min term 0, that's min term 5, and that's min term 4. So we need to declare 3 wires. Let's call them W1, W2, and W3. Okay, so let's start writing the code. Oops. How do I delete? Yeah. We have, let's name it module tutorial 5, question 1. We have A, B, C, and Y. Define your inputs. Input A, B, C, and then output Y. And we need 3 wires, wire W1, W2, and W3. Okay, so structural modeling using gate primitives. We'll start with the AND gates, or before the AND gates, we need to create inverters for A, B, and C because we need them in this gate. So we write not, let's call it N1. The output of N1, oh, I need to create more wires. So let's call this A underscore bar, B underscore bar, and C underscore bar. If you want to see those in this figure, A will give me A underscore bar, and so on for B and C. Okay, so not in one, will output a bar, and will take a as an input. Remember that in built-in gate primitives and even in user-defined primitives, the output will be listed first. Okay, so this will output a bar and will take as input a. We'll do the same for B and C. So let's call this N2, gate N3. This will be B bar and will take in B. This will take in C and will output C bar. Okay, now we have the inverters. Now we can do the AND gates. So AND A1, and A1 will output W1, list the output first, and then the input is going to be A bar, B bar, and C bar. B bar and C bar. I have two more AND gates. So AND gate A2, which is this one, is going to take in A, B bar, C. This is A3. So this is, let's go, this is W2. Okay. W2 will take in A, B bar, C, and W3 will take in A, B bar, C bar. Okay, now we need to create the OR gate. I'm gonna say OR, O1. This is the instance name. This will output Y and will take as input W1, W2, and W3. In module. Let's just run to make sure we don't have any errors. We do have errors. Undefined module not, oh, all the gate primitives are not defined. Undefined external port C. Right, where is this? Line 5. Oh, I need semicolon here. But still, if these are not defined. Okay, so we still have an error at line 8. This is not defined. Oh, okay. Turns out this is in small letters. So and let's try. Maybe it will not work as well. Okay, so no errors. No errors for that. Okay. Okay, so this is the solution to question 1. طيب في أي سؤال؟ This is tutorial 5, question 1. Okay, anyways. طيب السؤال اللي بعده question 2. A multiplexing circuit that receives 4 inputs, each of 1 bit. So we have, that means a 4-to-1 multiplexer should be used, namely x0, x1, x2, x3, and one output z based on 2 selection line is 0, s1. Okay, is considered using tri-state buffers. طيب, first part A, draw the resulting circuit using tri-state buffers. B, using the following built-in gate primitives for trusted buffer, buff1 and buff0. Write a complete Verilog code to structurally model the operation, and then write the test bench given these conditions. So let's do A and B and then jump back to check the requirement for the test bench. طيب, we're going to draw the circuit and then write the code using structural modeling. طيب. Now, for a 4 to 1 multiplexer using tri-state buffers, we'll use a 2 to 1 multiplexer, and then this connects to another 2 to 1 multiplexer. This will be controlled with S0, and this will be controlled with S1. As you know, this is X0, X1, X2, and X3. The output is Z. Okay, so this is the 4 to 1 multiplexer in general. Now, each multiplexer should be implemented using a tri-state buffer or tri-state buffers. So we're going to have tri-state buffer here. This will be this will be S0 bar, and this will take in S0. This is X0 and X1. And then, so this design is a 2 to 1 multiplexer. Another tri-state buffer will be controlled the same with S0 and S1 and S0 bar and S0, which will take in X2 and X3, connect the output together, and then these two output will go into another 2 to 1 multiplexer. So this will go into a tri-state buffer, and this will also go to another tri-state buffer, connect these outputs, and these will be controlled with S1 bar and S1. This is output Z. Now, the most important thing about tri-state buffer that if you are connecting two lines this way, you need to make sure that at any given time, only one of them is active. So this have S0 bar and this have S0, so that's fine. Only one of them will be active. Same here and same for these two. There is another way to implement the 4 to 1 multiplexer using only 4 tri-state buffers, but you need more gates. Let's try to do it here. Wait, let me erase this part since we don't need it. Okay, so this is the first design. The second design will use 4 tri-state buffers, and I will connect all the outputs together. This is output Z. And we need to make sure only one is active at a time. This will take X0, X1, X2, and X3. Now for the controls, instead of having a single signal here, we're going to have AND gate at each input. And here we can connect the multiplexer select line. So this will be selected at S0 bar, S1 bar. This will be selected at S0, S1 bar. This is at S0 bar, S1, and X3 at S1, S0. Okay, so these, only one of them will be active at a time because this is all the combination of S0 and S1. Or you can also connect a decoder here instead of these AND gates. If you have a decoder ready, if you have a 2 to 4 decoder, you can just call it and use that. So connect the decoder. This is D0, D1, D2, and D3. and you connect S1 and S0 to the input lines. Since the decoder will have only one output active at a time, so this will work fine with tri-state buffers. Okay, so any one of them should be fine. Okay, let's go on and write the code. So this is module tutorial 5 question 2, which will take in x0, x1, x2, x3, and will output z. Do we need, we need also s0 and s1. Okay, define your inputs. Input x0, x1, x2, x3, s1, s0. And we have on output z. Do we need wires? We need wires. In this design, even in this one, we need wires. So let's call this W1, and let's call this W2. Okay, if we're gonna do this, we need 4 wires for the output of the decoder. It's gonna be W1, W2, W3, and W4. We're doing this one anyway, so let's define the wires. I need wire W1 and W2. Okay, I need 2 inverters for S0 and S1. So we need to make 2 more wires. This is S0 bar and S1 bar. So let's get the inverters first. This is not, let's call it N1, which will output S0 bar, and will take S0 as an input. Same for ايش هذا؟ I'm not sure what happened. So not S, not N1 will output S0 bar and will give me S0. Just give me a second. 1 second, guys. طيب, back to the question. We need to declare the first inverter, which will output S0 bar, and then second inverter for S1, S1 bar, which will take in S1. Okay, and then we need to declare 4 buffers. So we're gonna use buff F1. Buff F1 is gonna be a buffer with an active high control, and we also have buff F0. Actually, we don't need these. We can use buff F1 and buff F0. Let's do that. So this one will be buff F0 for S0 bar, I can use buff F0, and even for this one I can use buff F0. Also this one will use buff F0. So buff F1 and buff F0 الفرق بينها في الكنترول. تمام. So the first tri-state buffer buff F0, let's call it B1. This will output W1. It will take X0 as an input, and it will take S0 as control. Okay. Next one will be this tri-state buffer, which will be a buff F1 with the same controls. We only need to change the input to X1. And of course, the output should be still, the output is still W1. Okay. Let's copy these two and create these two tri-state buffers. We need to change the names. Okay, so B3 and B4. For these two, we still have the same control. This will be buff F0 and this will be buff F1, controlled by S0. We only need to change the inputs. So this will take in X2 and this will take in X3. Now, for the last set of tri-state buffers, first change the instance name to B5 and B6. The first one is going to be an active low control. So that's going to be buff F0. It's going to output Z. We'll take in W1 as input and will be controlled by S1. Second one will be also be controlled by S1 and will take in W2. It should
دكتور W2 ما كتبناها فوق.
Okay. W2 should be the output of this. Yeah. So that's W2 and W2. تمام. Okay, are we done? I think yeah. So we can end this module. So we don't need inverters. We can use buff F0 and buff F1. Let me clear that and compile, check for any errors. Okay, so no errors, but I need to remove these two wires because I don't need them anymore. Okay. Right, so this is part B of question 2. So we drew two alternatives for part A. You can use any one of them, and we did part B. Type. Now write a test module that simulates the above module under the following input conditions. Set data input lines to 1 0 1 0, or from left to right is 0 1 0 1 for the entire duration of the simulation. So we're going to fix these values, and then S1 is 0. We're going to change the selection line. It's going to stay at 0 0 for the first 20 nanoseconds, and then we change it to 0 1 and let it on for 40 nanoseconds. S1 is 0 equal to 1 0 for 60 nanoseconds, and then S1 is 0 equal to 1 1 for the duration of 30 nanoseconds before ending the simulation. 20 40 60 30. Let's try to memorize that. 20 40 60 30. طيب. Let's go back. Let's take this here. ايش حكايته هذا؟ الظاهر الباد. يا رجل. لا 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 لا. اوكي. paste. Thank you. طيب, let's write the test bench. So module test bench. Now you need to declare your inputs as regs. So that's going to be reg x0, x1, x2, x3, s1 is 0, and we create a wire for the output, which is wire z. Now we need to create an instance of this module in here. So write the module name, give it an instance name, UUT, and then pass the inputs as just as the same. If you're using the same variable names, you can just copy the definition to pass it in order. Okay, now inside our initial begin end, this is where the simulation will be happening. I forgot to add the time scale. So we write time scale. Let's make it 1 nanosecond. 1 nanosecond. هذه كانت slash ولا backslash? I don't remember. Maybe it's this one. Let's try it out. So our time scale is set to 1 nanosecond at precision of 1 nanosecond. So everything will be rounded to whole values. طيب, كم كانت التايم ستيبس؟ 20 20 40 60 30. صحيح, 20 40 60 30. طيب, and x3 is x1 is x0 is 1, بعد كده up to x3. So let's write x0 equal to x0 equal to 1, and then we're going to alternate this value. x0, x1, x2, x3, that's going to be 1 0 1 0. Yep. Okay, these will be fixed. الآن I'm going to change S1 and S0 every two يعني there will be a difference in the duration of time. So at the beginning S1 equals 0 and S0 equal to 0. We need to stay at this value for 20 nanoseconds. So we can write pound 20. Now, how is this going to be 20 nanosecond? You're going to multiply this value 20 by your time scale. So if your time scale is declared differently, this number will change. So 20 multiplied by 1 nanosecond, that means wait for 20 nanoseconds. Now let's change these values. 01 will stay for 40 nanoseconds, and then 10 for 60 nanoseconds, and then 11 for 30 nanoseconds, and after that we need to finish the simulation using the command $finish. Okay. To see the waveform, I think I need to use two more commands. Dump bars, I think. Then dump to, I think, out.vcd, is it? Let's check. Uh, we need to enable something. Yeah, open EP wave. Let's try. Dump vars. Forgot something. So we still have some errors. Non-standard system. Dump. You know what? Let me take it off and it will tell me what to do. Mismatch detected token are missing in 39. Hmm. Unexpected token at 39. Do I need a semicolon here? Yep, this is what we need. Ah, dump file. Okay, dump file. We need to add those. I can't see anything. To be open a new browser set. All right. Now check x. So x0, x1, x2, and x3 are all fixed. These 4 lines are fixed at 1010. S0, S1 are 00 up until for 20 nanoseconds. Is it changing for? Ah, yeah, this is 20 nanoseconds. Okay, and then it changed to 01 for 40 nanoseconds. So 20 plus 40 is gonna stop, or it's gonna change at 60 nanoseconds. And then at 60 nanoseconds, you're gonna have 10, which will stay for another 60 nanoseconds. So this will go from 60 to 120. At 120, we change it to 11, run it for 30, here up to the end of the simulation, which is 150 nanoseconds. So we did this part correctly. Now check. Let's check the value of the output. Now, if S1 is 0 equal to 0, 0, I should choose X0 and X0 equal to 1. So that's correct. Here, I'm choosing X1, which is 0. And notice that the output is 0. In this step, S1 equal 1 and S0 equal 0. So we're going to choose X2. X2 equal 1 and Z equal 1. That's correct. Last combination is 1, 1. We should choose X3. X3 equal to 0 and Z equal to 0. So our simulation is working fine. Okay, so let's run the same simulation, ولكن let's change the time scale. Let's say you wrote here, instead of 1 nanosecond, let's say you wrote 2 nanosecond. Let's say by mistake, and you used these time units. This means that this wait is going to be, instead of 20, it's going to take 40 nanoseconds. This will take 80, and this will take 120, and this will take 60. So always multiply this time unit by the time scale. This time unit alone means nothing in seconds. This is just 20 time steps. 20 time steps. How to know how long is your single time step? You're gonna define that in your time scale. Let's run that and see the values. Time unit must use a multiplier of 110, or okay, I cannot use 2, so I can write 10. 10 nanoseconds. So this will translate to 200 nanoseconds. This will translate to 400. This is to 600, and this is to 300. check the first change occurred at 200 nanoseconds, and then 400 nanoseconds after that, which is 200 plus 400, which is 600. You change the value, stay for another 600 nanoseconds, meaning you stop at 1200, change the values, and stay for 300 nanoseconds اللي هو إلى 1500 nanoseconds. You're gonna finish the simulation. Okay, so always remember that this is not in nanoseconds. Mostly we're gonna use nanoseconds, so sometimes you get confused that this will generate 20 nanoseconds of delay. No, this value should be multiplied by whatever you define as the time scale. If you define this as 100 picosecond, the first step is going to be 2000 picosecond, which is equal to 2 nanoseconds. Still, we have an issue. I cannot have a precision less than the time, or larger than the time step. Right. So check first one. It was running at 2000 picosecond. Why? Because it's 20 multiplied by 100 picosecond. That will give you 200 or 2000 picosecond, which is equal to 2 nanoseconds. And then 4000 picosecond after that, that's 6000. And then 6000 after that, which is 12,000. And then for 3000 nanoseconds, you're going to stop at 15,000 picosecond. Sorry, picosecond, not nanosecond, picoseconds. Okay, فالفكرة من الموضوع انه always check your time scale before يعني to know what these time units will translate into. Okay, so just multiply whatever number you have here by your time scale. Okay. Now this is for question 2. Any questions? Okay. We still have 2 more questions, which is question 3 and question 4. Question 3 is using structural modeling with bottom-up design methodology. Write the Verilog Editor description of a 3-bit adder subtractor circuit. You need to follow the approach outlined below. So bottom-up approach, meaning we're going to start from the half adder and ending up with the 3-bit adder subtractor. So part A, draw the circuit at a high level using block diagrams where necessary. Define a module of a half adder using built-in gate primitives. Define a second module of a 1-bit adder subtractor by instantiating the necessary number of half adders and any additional built-in gate primitives to realize the modeling. So this is just saying a full adder, basically full adder with يعني adder subtraction control. Finally, define a third module for the 3-bit adder subtractor by instantiating the necessary number of 1-bit adder subtractor circuit. Okay, so let me check question 4. This problem is comprised of the following 2 related questions. Using user-defined UDP of your own with minimal number of rows. Explain how to design a magnitude comparator of 2 inputs. كذا كذا. The magnitude result comparator result will be active low. Okay. What about this? Write test bench module for that UDP. Simulation start at 0 when all inputs are zeros. 10 nanoseconds for simulation. Okay, so since we have time for tutorial, instead of starting, I don't like to start a new unit or give a lecture on a tutorial class. So let's keep these 2 problems for later today. At 2, we're going to look at these 2 questions. Okay. If you don't have any questions, you can leave.
دكتور
هلا.
تايم سكيل يا دكتور، اذا كتبنا 1 نانو سكند سلاش 1 نانو سكند.
جميل.
ال1 نانو سكند الثاني هذه وش فائدتها؟
ال1 نانو سكند الثانية هي عبارة عن تقريب، يعني إذا رجعنا للكود let's put it back to 1 nanosecond 1 nanosecond 1 nanosecond. هذه الثانية إنه كأنها الأكيوريسي، يعني any number that you see in time units تمام round it to the nearest 1 nanosecond. معناه إذا كتبت هنا 20.4 if I wrote 20.4 time steps this will translate into 20. إذا أنا كتبت let's write here 39.8 let's write 60.2 and this is 29.5. We should get the same results as we did before. Run it. تمام.
يعني قربها يا دكتور.
قرب، حيقربها. This will stop at 20, 60, 120 and will stop at 150. ما تغير شيء. ولكن إذا غيرت هذه من 1 نانو سكند إلى 100 بيكو سكند 100 بيكو سكند نفسها 0.1 نانو سكند. تمام. معناته قرب إلى the nearest 100 بيكو سكند. So if I write these values الآن حتلاقيها تفرق. Run it. This will stop at 20.4 nanosecond. So if you check here, this is 20.4 nanosecond. when اي هذه this is 20.4 nanoseconds. This will be 60.2 because it's 20.4 plus plus كم كانت plus 40 point something. So anyways it will take in that point in account. الآن for the same precision if you put 20.46 this will translate to 20.5. ليش؟ لأن الاكيوريسي تبعك 100 بيكو سكند اونلي اللي هو 0.1 نانو سكند، فمعناته قرب لي الى اقرب 0.1 نانو سكند. هذه اذا كتبت 0.89 this will translate into 39.9. if you have 60.22 this will translate into 60.2. 29.51 this will translate into 29.5. If you want to include 2 digits after the fraction make this 10 picosecond which is 0.01 nanosecond. تمام. فهذا limit of rounding how many digits you want to round after your time unit. اوكي. ف 1 nanosecond 1 nanosecond حيعطيك whole numbers فقط. So if you keep it the same this will become 20, this will become 40, this will become 60 and this will become 20, this will become 30. اوكي. لانه حنقربها الى اقرب نانو سكند.
الأولى ما تصير 21؟
الاولى لا ما تصير 21 لانه you're gonna take only one digit after the fraction. So let's check it. Maybe I'm wrong. It should be 20 I believe. Let's see. Yeah, so it's exactly 20 nanosecond. فحياخد اول رقم بعد الفاصله فقط. اوكي.
واضح يا دكتور، يعطيك العافيه.
حياك. طيب for the rest if you don't have any questions you can leave.